The main way in which PCI interconnects devices to the CPUs is by making devices accessible in a manner that's similar to how CPUs access memory. The device registers appear to the CPU as memory locations at a specific physical address. So then, when the CPU writes to these locations, the integrated memory PCI controller realizes that this access, the access to this physical location, should be routed to the appropriate device. What this means is that a portion of the physical memory on that computing system is dedicated for interactions with the device. We call this memory mapped I/O. And the portion of the memory that's reserved for these interactions is controlled by a specific set of registers, the base address registers. So how much memory and starting at which address will be used by a particular device. This gets configured during the boot process, and it's determined how exactly it's done by the PCI configuration protocol. In addition, the CPU can access devices via special instructions. For instance, on x86 platforms, there are special in-out instructions that are used for accessing devices. Each of the instructions has to specify the target device, so the I/O port, and some value that's going to be stored in registers. That's the value that needs to be written out to the device or the value that will be read out of the device. This model is called the I/O port model. The path from the device to the CPU's complex can take two routes. Devices can generate interrupts to the CPU, or the other option is for the CPU to poll the device by reading its status register in order to determine, does the device have some data for the CPU? Does the device have a response to a request that was sent to the CPU or some other information? There are overheads associated with both of these methods, and as always, there are trade-offs between the two. With interrupts, the problem is due to the handling of the interrupt routine, the interrupt handler. There are the actual steps involved in the handling of the interrupt routine. There are certain operations like setting and resetting the interrupt mask, depending on what kinds of interrupts are allowed to interrupt the interrupt handling routine or not, and also some indirect effects due to cache pollution that's related to the execution of this handler. So all of these are overheads, but on the flip side, it is possible to trigger an interrupt as soon as the device has something to do, some kind of notification, some kind of data for the CPU. For polling, the operating system has a possibility to choose when it will poll at some convenient times, when at least some of the cache pollution effects won't be too bad. If that is the case, then that's great. Some of those overheads will be removed, but potentially this will introduce some delays in the way that event is observed and in the way that the event is handled. The opposite of just continuously polling will clearly introduce some CPU overheads that may simply not be affordable if there aren't enough CPUs in the system or if the system is busy otherwise doing other things. Whether interrupt or polling mechanisms should be selected will really depend on the kind of device that we're dealing with, on the objectives, whether we want to maximize things like throughput or latency, on the complexity of the interrupt handling routine and the characteristics of the load of the device. So what is the input data rate, the output data rate that needs to be met, and a number of other factors.